In this video, we're going to go through single replacement reactions. Now you're probably wondering, why am I looking at twilight and what does it have to do with chemistry? Well, twilight is a great example of a single replacement reaction. Okay, so spoiler alert, if you haven't seen Twilight, in the first movie, you have Edward the vampire, and then you have Bella the human, and they end up dating. Well, Bella has a friend, Jacob, who has the hots for Bella and wants to be Bella's boyfriend. So what happens in the second movie is Jacob, the werewolf, and Edward the vampire switch places. Now Bella is hooking up with Jacob. That's a single replacement reaction. So Edward the vampire and Jacob the werewolf switch places. That's a single replacement reaction. So when you have a single replacement reaction, you have a compound. So in the case of an ionic compound, you have your cation and an anion. And you're going to have either a cation or an anion outside of the compound. So one of two things can happen. So if you have a positive cation, it's going to switch places with the cation in the compound, like here. If we had an anion outside of our compound, it would switch places with the anion. So it's basically just coming in and breaking up the couple. So here's a better example without all the twilight in it. Might actually be a better example, maybe a worse example. So again, you're switching out with something in the compound, and something is getting kicked out in the compound. You're replacing something, hence the name single replacement reaction. So here are the steps. Step 1, figure out the charge of every ion in the reaction. If C is a cation, it will bond with the anion from the compound. If C is an anion, it will bond with a cation from the compound. So basically, positive is going to switch out with the positive, negative is going to switch out with the negative. Figure out the ratio needed for the new compound to be neutral. If B on the product side is diatomic, add a subscript of 2. So this is what I'm talking about right here. Whatever is by itself, if it is diatomic, it's going to have a subscript of 2. So iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, fluorine. Those are elements that are diatomic. You will never see them by themselves. So you'll always have I2 or H2 or N2. They'll always have a buddy. You'll never see them by themselves. An easy way to remember this element list is I have no bright or clever friends. And finally, balance the reaction. So let's take a look at an example. So in this case, we have magnesium and sodium chloride. Figure out charges. So magnesium is +2. Sodium is +1. Chlorine -1. So opposites attract. So magnesium cannot bond with sodium, but magnesium can bond with chlorine. So on the right side of our reaction, we're going to have magnesium and chlorine bonding. I need 2 chlorines to bond because magnesium is +2, so I need a total negative charge of -2 to make our compound. And then sodium is going to be by itself. And I'm just going to quickly check. I have no bright or clever friends. Sodium is not on that list, so I can keep going. Our last step is to balance. So we have magnesium, sodium, chlorine on both sides. One magnesium, 1 sodium, 1 chlorine. On the product side, 1 magnesium, 1 sodium, 2 chlorines. So to balance this, I need to start with the chlorine. So let's put a 2 right here. That 2 distributes to the sodium and the chlorine. So this now becomes 2. And now I have 2 chlorines. So my chlorines are balanced, but now I need to go fix sodium. So on the left side, I have 2 sodiums. On the right side, I have 1. So if I put a 2 here, 2 times 1 becomes 2, and now I'm balanced. Let's look at another example. So we have potassium iodide and bromine. Let's figure out charges. So we have potassium, we have iodine, and we have bromine. Potassium is +1, iodine is -1, bromine is -1. So bromine and potassium are going to pair up because they're opposites. And the cool thing is they are the same, so I can just write these together. So potassium bromide, and then iodine is going to be by itself. Let's go through our checklist. I have no bright or clever friend. So iodine is on that list, can't be by itself, so I need to add a 2 here. Let's balance. We have potassium, we have iodine, we have bromine, potassium, iodine, bromine. 1 potassium, 1 iodine, 2 bromines, 1 potassium, 1 bromine, 2 iodines. So our iodines aren't balanced. I have 2 on the right side, 1 on the left side. So let's put a 2 here. That 2 goes to potassium and the iodine. 2 times 1 makes that 2. 2 times 1 makes that 2. So I fixed iodine, but I just broke potassium. So I have 2 potassiums on the left. I have 1 on the right. So let's put a 2 right here. 2 distributes to the potassium and the bromine. So 2 times 1 is 2. 2 times 1 is 2, and we're balanced. All right, let's move on. So here we have aluminum, we have hydrogen, and chlorine. Aluminum is +3, hydrogen +1, chlorine -1. So aluminum is going to match up. It's positive, so it's going to attach to the chlorine here. So we will have Al. Now, aluminum is +3, chlorine is -1. So to balance those charges, I need 3 chlorines. So aluminum chloride, and then hydrogen. I have no bright or clever friends. Hydrogen is on that list, so it needs a buddy. So we've got aluminum, hydrogen, chlorine, aluminum, hydrogen, chlorine, 1, 1, 1. On the right side, 1, 2, 3. Let's start with the hydrogens. So I have 2 on the right, I have 1 on the left, but I'm noticing here that chlorine and hydrogen are next to each other, and I'm just kind of looking ahead here. I noticed that I have a 3 down here for chlorines. So if I put a 2 here, it might fix the hydrogens temporarily, but I'm gonna have to change that in a second. So let's just table that for a second. So let's do chlorines instead. We have 3 on the right, I need 3 on the left. So if I put a 3 here, 3 times 1 makes this 3, and that makes this 3. Oh, now I still have a problem. So I have 3 here and 2 here. So we're going to need a least common multiple. It's going to get a little bit more complicated. So we're going to need a least common multiple of 6. So instead of making this 3, let's make this 6. And when you're balancing, you might have to go back and forth. It happens. So 6 times 1 is 6. Let me go back and fix this. 6 times 1 is 6. Okay, so now we got it. So now we can fix the hydrogens the right way, and the chlorines. So we have 6 on the left, I have 2 on the right, so let's put a 3 here. 3 times 2 makes this a 6. And I need 6 chlorines. So to do that, I'm going to put a 2 right here. 2 times the 1 aluminum is 2. 2 times the 3 is 6. On the left side, I have 1 aluminum. On the right side, I have 2. So let's put a 2 right here. Wow, that was a lot of work. And balanced. All right, last one. So we have magnesium, we have sodium, and then we have nitrate, NO3. So magnesium is +2, sodium is +1, nitrate -1. So magnesium is going to pair up with nitrate. Opposites attract. So I will end up with Mg, and then I need 2 of these nitrates, so it'll be NO3 and then 2 on the outside, and then I have sodium left over. I have no bright or clever friends. Sodium is not on the list, so I can keep going. So I have magnesium, I have sodium, I have nitrate. I have magnesium, sodium, nitrate. 1 magnesium, 1 sodium, 1 nitrate. Don't let that 3 confuse you. That's part of the nitrate. On the right side, 1 magnesium, 1 sodium, 2 nitrates. 2 nitrates on the right, 1 on the left. So let's put a 2 right here. That goes to the sodium and the nitrate. 2 times 1 is 2. 2 times 1 is 2. On the right side, I have 1 sodium. On the left side, I have 2. So let's put a 2 right here. 2 times 1 is 2. Done. That's single replacement reactions.